Hello students, as indicated in the last module, in this module we will try to derive the detection probability of a code acquisition system for the direct sequence spread spectrum communications. And we have seen, we will refer the same block diagram that we have seen in the last module, and this is the block diagram of a single dwell time PN acquisition system with your non-coherent detection. We understand that the non-coherent detection involves no information about the carrier synchronization. No carrier synchronization is not done. So, no information about the carrier phase is known to the receiver and known to this acquisition block at least, and as it is hence it is a non-coherent type detector involved. In a non-coherent type detector, we have a band pass filter which is band limiting the incoming signal up to a bandwidth of capital B, and XT we saw in the last module that it is having a form of the received signal, intended signal plus the noise. Noise is having a two-sided power spectral density of N0 by 2, and we saw that the square law enveloped detector output is having a non-central chi-square distribution in the presence of signal and central chi-square distribution in the absence of signal. If I put the capital A is equal to 0 in the expression of the SNR, and this gamma actually present or non-present is equivalent to the signal present or signal non-present, and if we feed this YT into this integrated dump receiver, where the sampler we assume that is running at the Nyquist rate, that means at the rate of 1 by bandwidth capital B, the T is equal to, and when it is sampling like at that bandwidth, we saw that the distribution, the probability density function of this Z is also having a similar pattern of non-central and central chi-square distribution with some different Bessel functions, and that also was related to the presence and absence of the signal, and based on that we also derived here the value of the probability of false alarm, which we thought that inside this threshold comparison, suppose there is a threshold defined, and if the false alarm is typically saying that when the signal is not present, how many times the incoming signal Z is crossing the value of the threshold and falsely detecting that as if signal is present. And further on further derivation, what we did is we normalized both Z to Z star, and we also normalized this threshold from eta to eta star, normalized it by means of our 2 sigma square by n b. 2 sigma square was the variance of the noise sample. For the reference, I have written here the expression of the Z that we could see that time because of the sampling at this Nyquist rate. So, it could be approximately written like this. So, that was a recap of the last module, and from here onwards we understand completely what is the probability distribution function of this Z in presence of the signal, in absence of the signal both. Going by the same philosophy, the way we devised in the last module the probability of false alarm expression, going by the same philosophy we will now derive the probability of the detection. Okay. So, we have seen these two expression. This were the expression of the PDF of Z when the signal present and signal absent. So, by substitution of capital, when we substituted capital A is equal to 0 in the expressions, and gamma was given by your S square divided by the N0 into B, and as your sigma square was given as N0, sigma square was given as the noise variance, it was the noise variance, and we had substituted this noise variance by substituted the noise variance, and then we got the sigma, substituted the sigma in the gamma, and we finally got the finally actually when capital A is becoming 0, the gamma is absent, and we can put the gamma value 0, gamma equal to 0 in the expression of 1.11 to derive 1.12. And if these are there, we develop the probability of Rawls-Salem using the expression 1.12. Now, we will do the same philosophy that it was earlier. The detection probability is basically given by the integration which is running from eta star to infinity of probability of z star dz star, where this probability of z star is basically now will be substituted from the signal present PDF of z. As we understand, this integration is tough to achieve because upper limit is up to infinity, and then hence we have redefined it in terms of 1 minus 0 to eta star, and this is the final expression that we are getting for the detection probability using the expression 1.11. Now, we have to go ahead with some assumption. Let us consider that this NB, what is this NB? NB was there inside the probability distribution of the Z, and hence it is here also. NB, if you remember, NB was the number of the samples that you were getting. The number of the samples we wrote given by number of the samples was written as tau d divided by capital T. 1 by T is equal to B. So, basically it is B into tau d. So, see that I told in the last module that how many number of the samples are based on the number of the samples you are getting at the output of the sampler. The probability distribution of this Pz can be largely approximated. For example, if the value of the NB is too large, then it can have approximated by a Gaussian distribution. We will proceed considering that Pz is having a Gaussian distribution because NB is very large, and hence we can redefine the Yk. Yk will be defined as Yk star such that the Ykt that we were getting earlier, it is normalized with the noise variance once again, and hence these were the two PDFs for Py. Now, in terms of Yk star, I can get these two. Remember 2 coming because 2 expressions are coming because one is for signal present and another is for signal absent. Where was this Y? This Yt was, if you remember correctly, this Yt was at the at the output of your square law detector, hence at the input of your integrate and dump circuit. So, now if this is the situation for your Yk, I can also get from the expression of Z that we saw in the last module. This approximation we did in the last module, where my NB is equal to tau d by capital T, and in terms of I can rewrite actually this expression in like expression 1.17 by substituting Z as Z star, and Ykt is will be also substituting by Yk star by substituting the values of Z to Z star by using the relation of Z to Z star and Y to Yk star. And remember, if the samples are actually sampling is done at the Nyquist rate, and if we hence the previous assumptions holds good, all these Yks, they are all the independent random variables, they should be. And if the NB is too large, then these Yks will be all the independent random variables, and hence this Z star will be Gaussian distributed. I mentioned it earlier. If it is Gaussian distributed, the mean of this given by the Z star bar, it will be simply the NB Y star, and the variance will be Y star, it is not Y star, it will be Y star or Y star bar, whatever you write. It should be Y star bar, and the variance will be the sigma Z square equal to the NB into sigma square of this Y. So, it is basically the NB times multiplied with the mean of this Y and mean of variance of this Y. and lot of research papers are available who shows that this mean and variance will be easily obtained, and prior to that revisit the probability of I k star in terms of the mean and variance. So, these two probability equations in terms of your mean and variance would look like this, and from here actually this mean and variance of these PDFs. So, we understand that first we have to now get the mean and variance of this y k star, y star, and as well as the variance of this y, and that will be brought from the previous PDF expression given and developed earlier, and a lot of literature available which shows that the probability mean and the variance when the signal is present for with respect to these two PDFs, when signal is present, then the mean will be given as 1 plus gamma, and variance will be given as 1 plus 2 gamma. When the signal is absent, so put directly gamma equal to 0, you will be ending up with the mean and variance both equal to 1. If this is the situation, going by the fact that z star bar is nothing but the mean of this z star bar is nothing but n b times the y star bar, and hence it will be simply multiplied by n b into 1 plus gamma when the signal is present, or only n b when the signal is absent. So, the mean value is varying from n b into 1 plus gamma to the n b value. So, n b multiplied by 1 plus the signal to noise ratio when the signal is present for the mean of the z star bar, and it will be simply governed by the number of the samples when the signal is absent. Come to the variance section, we substitute actually the value of the variance of the y multiplied with the n b for the computation of the variance in the presence of the signal, and put gamma equal to 0 when we calculate the variance in the absence of the signal for z. So, these are the very important 4 parameters that will be helping us to derive the expressions further. Now, we are ready to redefine our probability of false alarm and probability of detection that was derived earlier. Using the Gaussian assumption, we understand the probability of the false alarm will be governed by the Gaussian distribution given here, and if it is Gaussian distribution which can also be approximated by a q function, and we write actually the expression inside the q as just the beta, and q x is a Gaussian probability integral here given, and if the probability of false alarm is given because of any synchronizer design usually have a constraint on the probability of false alarm always, given the minimum allowable probability of false alarm, this beta can be, you can define this beta. So, there is a combination and relation of this chosen normalized threshold inside the verification algorithm and the number of the samples that you are having in your hand. There is a relation between these two with the probability of false alarm. And corresponding detection probability, he will be also given by this, and here you are representing all the mean and variance. See, actually here variance was only n b, and here it is coming 1 plus 2 gamma like that, and the mean was here n b, here I am substituting it by 1 gamma, variance is actually 1 plus 2 gamma. And the q function is simply similarly you can come up with a q function in terms of the beta represented here, you can actually write in short form of the detection probability. That remember, inside the detection probability analysis already not only the gamma, the signal to noise ratio is involved, already the probability of false alarm section, I mean it is involved. So, beta is actually a function of this eta square and the n b. So, the threshold is also coming in addition to the n b and the signal to noise ratio in the expression of the detection probability. And if I substitute try to write the detection probability in terms of the false alarm probability, and I substitute all the parameters of this detection probability by the system parameters. For example, n b was equal to capital B into tau d, and gamma was equal to a square divided by n 0 into b. If I write like this, then finally, we will be ending up with the fact that we were claiming at the beginning that look, the detection probability given a false alarm probability, detection probability is a function of the dwell time. So, even if actually I am giving you the detection probability and false alarm probability, and if it is a function of dwell time, and then again the acquisition time is also a function of your probability of detection, probability of false alarm, and your probability of false alarm, and as well as the dwell time tau d, then you cannot actually easily, even if you know the detection and probability and false alarm probability, you cannot arbitrarily choose the dwell time, so that the mean acquisition time is achieved, because if you arbitrarily choose the dwell time, definitely the PD value will be changing. If PD value changes, then the acquisition time will be something else. So, choice of the tau d is such that even if you know the PD, it is not so easy to do the optimum, do the proper selection in between the tau d without changing the PD. So, it is not straightforward to do the pick up some acquisition time or to do justice with the mean acquisition time just arbitrarily picking up any tau d value. You have to have a very close observation between the PD, the way PD is changing with respect to tau d, and then accordingly the given probability of false alarm and given gamma value, how that is varying, and based on that how the acquisition time, then the acquisition time will be calculated. Remember, up to this we could define the relation, nice relation of the detection probability. We understood actually how it should be calculated, taking a very simple example of a non-coherent square law detectors. And but this is wherever whatever we have derived here, we have several assumptions inside that. So, one by one we will try to see whether those assumptions are valid in practice or they are really not. Remember, number one assumption that we did is that PD and PFA, this gamma, this bandwidth, tau d, all can be determined, and all a calculation of this implicitly assume that only one cell in the entire search satisfied the condition that the signal is present. So, out of, even if it is a multiple dwell time based detector, even if actually the detection process whole stuff we have calculated, considering that at least one cell is having the entire search process satisfied that the signal is present. So, even if actually one time the signal is present, we could detect, we have we are done, and then we will define the detection probability. Okay. But in actual what was done? In actual it was done that the PN correlation curve, if you observe, the correlation graph actually exists over an interval of plus minus 1 chip around this peak. So, this you have to actually look into the fact that detection can also get locked here or here. It may not be exactly the peak. So, you may get actually anywhere within the plus minus 1 chip duration, and that is why actually you are not always going to get the good peak value, peak SNR value also, because the value of the capital A here is not same than the peak value of it. So, hence it will vary the gamma value inside this detection probability. How much that variation will be, let us have a look. So, typically the systems that we have designed already, they are designed based of the worst case correlation. Actually, the situation is such that the acquisition that is getting achieved, that will be within half of the period of the chip duration. So, we understand the correlation peak is spread over the plus minus 1 chip duration, and even if you get the code acquisition, that will be within a plus minus half of the chip duration, and hence the correlation points will be within the 1/4 chip duration. So, 1/4 of the chip duration time here and 1/4 of the chip duration time there, you will be able to get. So, after acquisition you are getting a correlation peak spread over 1/4 of the TC by minus TC by 4 minus TC by 4, it is minus TC by 4 to plus TC by 4 duration. So, over this chip duration you are really not getting the peak value of the autocorrelation function, you are getting actually the 75% of it. So, if we substitute the 75% of the peak value of the autocorrelated output, the value of the square you are not 1 here, it is only 0.75, and hence you will get a loss of the dB or in the SNR by an amount of 2.5 dB. So, the detection probability will be definitely actually be affected by a redefined signal to noise ratio. It is a that is why we call it an effective probability detection, we do not call it a true detection probability. So, the expressions that we have got in the last few slides, PD and PFA, they are the actual detection probability and actual false alarm probability, whereas in practice we will always get the effective detection probability, which will be computed as this. The expression of this detection probability, effective detection probability, will be given by equation 1.24, where the first part is representing the probability that you are detecting the signal present on the first correlation point. By means of first correlation point, what I mean is you are at minus Tc by 4. Okay. So, and in the second correlation, second part of it is telling what is the joint probability of detecting the signal on the first and the first correlation point, as well as detecting the signal on the second correlation point. So, you have to take the effect of the both, and hence our earlier detection probability for this, when the basis of the signal present will be given, will not be the only way to declare that this is a detection probability. Now, the computation should go like this. You compute first the probability of the false alarm, going by the equation 1.21, which is exactly similar the way we defined earlier. Then you compute, use this beta to compute the theoretical detection probability following the expression of 1.22, which was also defined earlier. You may utilize actually you may see all the substitute all the values of the gamma and all, and this for specified PD dashed, find PD from this 1.24 and degrade the given nominal value of the gamma by 2.5 dB and solve for this NB now to get. So, now you solve for NB to get actually the value of the dwell time tau d, and you can get the value of NB also. Then from there you can get the approximate idea about the tau d. So, the case is something like this. For you now you will be getting PD P dash d finally. From there you can calculate the value of the PD, and once you are getting the value of the PD, then you understand actually what is the value of the beta to get actually the expression of the PD. So, but you understand the value of PD, and from there you have the redefined value of the gamma. Gamma is not exactly equal to the one exactly effect of the whatever scenario you are dealing with earlier. You have nominal value of gamma by 2.5 dB, and finally you from there you can calculate the PD. So, now PD is actually having the effect of P dash d in that sense, and determine the dwell time. Now, once you are getting the value of NB from this expression, you can find out tau d, and B is given dominated by the given band pass filter bandwidth. So, this is the way we actually in practice should compute PD. Another effect that we should discuss at last, that is a modulation distortion effect. The modulation distortion effect means the PN modulated carrier, it is also biphase modulated by the data. So, when we are using the pre-detection bandpass filter, which is having a bandwidth of B to the data rate R. So, once you are using a bandpass filter and you are passing a signal through it, so it will distort the incoming signal to a great extent, and once actually the distortion happens, there will be a huge reduction in the power of the modulated signal at the output of the filter. We can quantify that reduction factor by M2, which is computed by this expression this, where this H 2 pi f H j 2 pi f, it is the equivalent low pass transfer function of the pre-detection bandpass filter, and SMF is the power spectral density of the data modulation. So, define, see that there will be a reduction by an amount M2, which is a function of the power spectral density of the incoming signal and also affected by the incoming signal affected by the equivalent low pass transfer function of the bandpass filter. and thus the value of the A square that is used inside the signal to noise ratio calculation, that should be multiplied by this M2. So, you are not getting actually A square. Earlier we saw that because of the code acquisition getting within plus minus Tc by 2, there is a reduction in the SNR value. Here there is another further reduction in the SNR value, because we are not getting, there is an effect of the band pass filter pre-residing the square law detector, and its effect is such that it with the A square, the power of the signal will be reduced by an amount of M2 that we have to capture in the calculation. The last effect is not only there is a reduction in the on the signal. So, last two effects we discussed about the reduction on the signal power. Remember, when we do the dispersing process inside the receiver front end, the noise spectral density reduces, because noise spectrum it expands, noise spectrum expands by the dispersing process itself, and the spreading of the spectrum reduces the spectral height, and effectively actually it reduces the spectral density. So, N0 you cannot consider as a direct N0, hence there will be an effective noise spectral density like the effective detection probability, and we define the effective noise spectral density as N0 dash, which will be now given by the expression 1.26. So, then your basically again actually the effect of the band pass filter is coming into picture, and the envelope means instead of actually simplicity for calculation, we have considered that the line spectrum is approximated, can be approximated by the envelope of the noise, and thus again effective signal to noise ratio computation will be done by multiplying A square with M2 and substituting the N0 by N0 dash. How we will see next. Look that now going by the similar terms, we will redefine the noise signal to noise ratio as effective signal to noise ratio and represent it by gamma dashed instead of gamma. And as we understood that because of the effect of the band pass filter, the power of the signal will be multiplied by M2, there is a reduction of the signal power. N0 will be substituted by N0 dashed, bandwidth is remaining constant. There is another factor coming as capital L, which is also getting which is considered to be a loss. What is that loss? We understand M2 and N0 will be given by this as shown in the last two slides. This L is nothing but because of the cheap misalignment, residual offsets that you are having, and that alignment, if that alignment is given by an amount of tau with respect to the cheap duration Tc. So, there will be a loss because of that remaining residual error. So, the loss due to that residual error is incorporated by the factor capital L in the expression of 1.27. So, the originally the whatever the gamma expression that we have put in the calculation of the probability of false alarm and especially the detection probability analysis, now we understand that if we try to get the true detection probability, we have to modify the computation of the signal to noise ratio by the effective signal to noise ratio by taking care of the effect of the band pass filter on the signal on the data modulated section and the effect of the dispersing process on the noise power spectral density given by the equation 1.27. Then only you will be able to calculate the proper or the correct effective detection probability.